For centuries, mathematicians have been captivated by a seemingly simple question: how do you best pack identical spheres into a given space? This is known as the sphere packing problem. While we've nailed the optimal arrangements for dimensions 1, 2, 3, and even the more exotic 8 and 24, finding the densest packings in other, particularly higher, dimensions remains a huge challenge. But recent breakthroughs are changing the game, with tools from graph theory and surprising links to how we transmit information. For a long time, the densest sphere packings we knew in many dimensions were very regular, like crystals. But in late 2023 and early 2024, a team of 4 mathematicians, Marcelo Campos, Matthew Jensen, Marcus Michelin, and Julian Sahasrabudhe, achieved something remarkable. They provided the first improvement in 75 years to a key measure of sphere packing density in high dimensions. What's really fascinating is their approach. Instead of looking for perfect order, they embraced disorder. They used graph theory. Imagine you discretize space, perhaps using a random scattering of points that could be sphere centers. Then, you build a graph where these points are vertices. An edge connects any 2 vertices if spheres centered at those points would overlap. A sphere packing, then, is what's called an independent set in this graph, a collection of vertices where no 2 are connected. The researchers developed new tools to find very large independent sets, even using a clever iterative method called the Rödel nibble. This suggests that in very high dimensions, the best packings might be amorphous, not neatly arranged lattices. Now, you might wonder, why bother with packing spheres in, say, 50 or 100 dimensions? It turns out this has big implications for information theory, specifically for error-correcting codes. When you send a message, like an email or a photo over Wi-Fi, it travels through a noisy channel where errors can creep in. To protect against this, messages can be represented as points in a high-dimensional space. Each point is the center of a conceptual sphere. The game is to pack these spheres as densely as possible without them overlapping. The radius of these spheres represents how much noise the system can tolerate. A denser packing means you can either transmit a larger vocabulary of messages or have greater noise tolerance. So, better high-dimensional sphere packing directly leads to more efficient and reliable data transmission, think cell phones, Wi-Fi, and data storage. The sphere packing problem is far from solved for most high dimensions. We had Marina Vyazovska's incredible work in 2016, which definitively solved dimensions 8 and 24 using sophisticated mathematics like modular forms, but these are often seen as special cases. Research continues on many fronts. Mathematicians are constantly working to narrow the gap between known achievable densities and theoretical upper limits. There's also a big question: are optimal packings in most high dimensions ordered, or are they disordered, as the new graph theory methods suggest? New algorithms are also being developed to explore these packings numerically. The connections to other fields, from Fourier analysis to physics and the structure of matter, keep providing fresh insights. So, the study of high-dimensional sphere packing is alive and kicking. These new graph-theoretic approaches are not just deepening our understanding of a fundamental geometric puzzle, but also hold the promise of enhancing the technologies that define our modern digital world.